Okay, so we're back where we are, and I will share this link out again somehow if I can figure out how to share the link. I think there's a share button here, but is that share for, I wonder if that's a share for share, copy, and Python programming live stream. N-body simulation of galaxy mergers. Spell simulation, right? So I think it's all there and potentially working. I'll actually click on it and click on the stream bit and just check. Probably be some background noise. Okay, the word galaxy mergers. And everyone should be able to post in the chat things as well. So let me just hit close there. So you should be able to post in the chat too if you're there. Now, where we got to on this, and I need to get some more tools out. I figured I need to get some more drawing tools out. Let me just get rid of this. Don't need that there. Which is, we're down at this bit, and I was going to just start doing all of this myself, but I thought I might as well just go and do it live so that everyone can see. And one of the comments that I had was I'm an R too much. So the reason why, there's a caveat for all of this, which is that everything here is done completely live. I've done no practice at all, no pre-work at all. This is effectively like real coding, as opposed to the videos that you see, the 1 minute videos that you see, and they always work, and sort of like, you know, everything's already up and running, and it all goes, there was one of them, it all goes seamlessly straight away, and this is how you do it and it works. And even on the like your 10-minute videos and so forth, it's the same thing where something's been pre-prepared and, you know, it's been pre-made, and I can do those things as well, which is, it's nice sometimes. Then you cut out all of your ums and ahs and all of the faux pas and all of the things that you said that were wrong that you'll probably cringe at 3 weeks later. This is just completely live, as is, like literally coding as is. And where I get stuck, I get stuck, and where I don't get stuck, I don't get stuck, and I'll be going through the documentation and so forth, just literally in real time. If there's any comments, for example, if the font is too small, just let me know, and so forth. But just, I guess maybe if I've got some of the stuff up, I don't have that one up. That was kind of, we were talking about moving something in pygame, like an object in pygame, and I don't even think now I could move it. No, I can't. Well, I could move this new square, but basically in a game you can kind of like do this, which is quite simple. So like move your element around somewhere in the actual game. But when you're doing a simulation, it might be a case that the simulation is quite simple, but if you're doing a simulation and it's got lots of calculations that go into it, it might slow the code down. And we worked out, broadly speaking, that there were roughly, I don't know, it's probably 15,000 wrong color there. Let's just get that in the right color. I think it's just, yeah, that's fine. There was probably about 15,000, just crudely speaking, calculations per cycle, which is fine. Computers handle this quite well. Only that, so I'll make that a bit smaller, 15,000 cycles per calculation. Only that we know that we are running at 60 frames per second. Well, it's a maximum of 60 frames per second, so that's our upper limit. But if we pull out the calculator, which I probably still have, that's 1/60, so it is, I'm too lazy to do it, copy, which is, that's number of frames per second, which is this, seconds for each frame. Now, even with a great computer, 15,000 calculations in 0.016 of a second. If we do that, that will be, or how many calculations are we going to do per second? We'd have to do, just crudely speaking again, where's my little calculator? Over here. It'd be 1,500, not 15,000, 1,500 calculations divided by 0.017, basically, because 0.016 rounded up, is about 88,000 calculations per second. So that would give us here 88 and that would be if we were doing, this was for 100 particles, right? So that's what that's for. Let me just expand that little text box. So that's for 100 particles. I should actually write it down somewhere in the actual code itself, just sort of like, so we've got a back of the envelope or something somewhere. So let me, I'll probably make, maybe I'll make some notes. So make some notes at the bottom. I wonder where I should put some notes. So maybe I should make a little readme.md or something like that, so that I can actually operate there. Because at the moment what I'm doing is I'm operating here using LibreOffice Draw to draw some pictures, and then I've got a paint over here on the side, and I might actually copy all of this text. What I'll do for now at least is I'll just stick it into a text box here, just in LibreOffice Draw, so it's at least somewhere. But basically we've got this 15,000 calculations per cycle, and this is for 100 particles. That was crudely speaking, because, and the reason why it is that, maybe I'll put some more context down there. This is for 100 particles. This is for 100 particles, and the reason it's that many calculations, tab, because, and of the following reasons really, a few different loops, and also, so that's number one, which was, there was a few different loops, and number two, there are 3 dimensions, probably about 4 different loops, 3 dimensions. So every particle, we're doing a calculation on every single particle, because this is for 100 particles. We are calculating for every particle. That's what's actually happening. So we're calculating for every particle, and there's 100 particles, and there's 3 dimensions, which means three calculations at least per particle. And that's gone over, spilt over the edge, and I'm just using a text box here at the moment. Wonder if I can make that a little bit bigger. There we go, just about squeezes in. Close the brackets. It's gone over the line size. Okay, let's just make that a tiny bit smaller at this moment. Or so I can make, maybe I can make the text box a little bit, just a little bit bigger. There we go. I don't want to go too far, but that's what it is. Well, as soon as I put the full stop, I can get one more dot in there. And there's a few different loops. So we're doing 300 and then times by this. When I say a few, I think it was about 5, roughly. 5 different loops, and we can actually see what the loops are as well, and sort of like list them out. But just off the top of my head, loops 4, we needed to calculate the center of gravity in 2D or 3D. So we needed to do that. Basically everything's going to be in 2D or 3D. From the center of gravity, we needed, we also had that, we had the velocity, we needed, okay, the next bit we need is a change in position. That's what it's all about, by the way, because this is the thing that we want to draw. Right, so that's the thing we want to draw. Number 3 there is we've got the change in position and change in position is computed from the change in velocity. We've also got the change in velocity. But this change in velocity comes about from the force on any particle I should say planets, not particles, because actually this is a simulation of galaxy mergers, and these are supposed to be very, very massive objects, not tiny little ones. So I'm referring to a planet as a particle at this point in time. Force on a particle, and from the force on the particle, we can then compute the acceleration of the particle. Right. Again, this is all, everything here is all 2D and 3D, right? All of it. It's either 2D or 3 dimensions. We've chosen, still, even though we're rendering our view in 2 dimensions, we're choosing to go with 3 dimensions, or at least doing our computations in 3 dimensions, because it will carry over, not might carry over, it would carry over. So each one of these is 300, 300, 300, 300, 300, 1, 2, 3, 4, 5. That's 1,500 calculations just there alone, and we are attempting to do this within 0.016 seconds for each frame. 0.16. I don't know how to do the reoccurring sign because normally you put a dot on top. 0.16. I just put 0.17 seconds for each frame. There we go. Give ourselves some flexibility. So we did our 15,000 divided by 0.17. That's where we've got our 88,000 calculations per second, which is a humongous amount of calculations. And if we have more than, say, well, kind of like we observed already, that. And we can see this anyway when I say this observation. I can actually run it here, F5. Actually run this live, and I was trying to get rid of the lines, by the way. That's part of what the live coding is, but that's okay. That was with, let's just go down and have a look. I think it was with 50 particles. It's right somewhere down at the bottom. We'll actually start running the simulation here. We do our simulation. This line here is the actual simulation line, which we use 20 particles there, which was fine. But when we got to 200 particles, if I run the same piece of code, you can see the slowness, right? Slow. You know, it's kind of like bitty. So somewhere between 200 to, you know, I'll dare myself. I'm going to hit save first and Control S to save it. 400. We go for 400 particles. I think it might break it. I don't know. But 400 particles, we'd have to multiply that by basically 15 per 100. So we've got to multiply this one by 4 effectively. So that's 3,000, 6,000 calculations would be done for 400 particles. 6,000 calculations in 0.01 of a second, which is large to ask of many things, I guess, even of a modern PC. This isn't the best PC, but kind of like it's good enough. But there you go. You can see it kind of like going really slowly. But it is working. But look at the loop numbers. We've only done 11, 12, 13 loops. And that's what we were referring to. Close. It was even slow closing, actually. That was we were referring to over, I did have it there, where we said max. I'll make that red, that little bit. Oh, not red, but purple. There we go. 60 frames per second max. That's the maximum we've got. So now it's not even able to do the 60 frames per second. It's just slow down. That was to cap it so that it didn't go too quick. But now we're slowing down because it's just not able to compute fast enough. So just make sure everyone can see this. Right, okay, fine, yeah. So that's really it on that part. And as I was saying, we observe that the system slows down noticeably. Slows down between, what was it, between say 200 and 400 particles. So that's where it begins to become a little bit slow, and therefore we want to speed this up. Therefore, so we need, well, here it is, we need to simulate 4,000 of particles. There we go. And if I do, I'll probably save this file somewhere. Save, let's have a little look. I'm just going to save this somewhere. Programming, just saving the file, Python, and I've got to remember what I did this under. I called it physics, I think. I had a folder called physics. It will go into this folder. This is just the drawing, basically. And I'm just going to call it notes. It's an open office drawing, so that will go in there. That's kind of like saved now. So at least there's something to come back to, because before I had nothing to come back to. And the reason why I was going to do a markdown file here, but actually it really needs some background, because basically we're missing out on, you know, some of the things just in general that are kind of like useful to understand. And actually one thing that I should show is, where's that got big gaps over there? I wonder, let's have a look. Everything was as is. Okay, let me just shovel all of this up to the top of the page. There we go. I shouldn't really put it in a drawing object, so I should actually put it in a proper document. But then there's a lot of drawings, so it's okay for what it is, just because we will be doing lots of drawings. But, well, actually this bit that I'm shoveling around is a bit that's going to be of the next important, because we were talking about reminding ourselves that one of the reasons that it's slow is that I'm using a Python list, and it's very convenient, but very inefficient. So add elements whenever and wherever we like. And so what we have really is something like this, which is, on the one hand, we've got convenient, and on the other side we've got efficient. So they're the two ends of the spectrum. You don't get both of them. I'll even write just about. They're the two ends of the spectrum. You don't get both of them. But basically, a Python list lives here. So a list. I'll just call it a list, not a Python list. So a list lives here. I wonder what size font that was. Right. Don't like 13 because it's an unlucky number. There you go. That's 14. That's 14. Okay. Let's just make that one bigger. Right. So that's a list, and this is. Let's just copy this here. An array. Right. Arrays are less convenient, but they are just much faster. So you might say, why don't we always use arrays? Well, the reason you don't always use arrays is because they're not convenient, and you can't write them out quickly, and you have to like pre-structure them. It's not that difficult, but you have to know the size of your array beforehand in order to declare it to reserve the block of memory. That's the efficiency gain. The argument here is that you should know it. For the most part, like, why don't you know the size of the arrays? But then there's dynamic programming where the arrays just change as and when you need them, because so you kind of like, it's the concept of that you don't need a fixed size because you don't know what it is, and you'll just add and chop and change as you need. But you give up a lot of stuff on that. So I can sort of like, I think, there we go, something like that. So we've got this trade-off. We can't have both. We can't have, unfortunately, we want to, but we can't have efficiency and speed at the same time. No one gives us that, no language that I know of. It's always swings and roundabouts with these things. So that's kind of like where we're at. Fill it. Let's make it a slightly lighter colour there. There we go. That's sort of like where we're at. So I wonder if area. It's kind of like this. If I can get a gradient looking sort of thing, which is like that. I guess it's good enough. Maybe if I make this a little bit more red or something, there we go. And then hit OK. There we go. That shows you like one side efficiency and the other side convenience, and you can kind of like go and pick and choose. I have a little attempt at area. Let's have a go again. Not having yellow, but sort of like going to a lime. So okay, it's hard to tell what it's going to look like. Okay, I'm going to hit undo because it's put these zigzaggy lines in there. Area. So I don't know why how the zigzag lines got in there, but they did. Okay, doesn't matter. I'll leave it as is. Cancel. Don't want to change anything or do anything. That's fine. We just don't get both, basically, which is fine. So I'm going to go back to the code now and start working on it, which is basically this numpy array. And I have to remember now, and I'm doing this in the test module. So I've made this function, define particles, and I'm hoping that it returns back an np.nd array. I think that's a type that I want to get back, and I can kind of like go to, I guess I should open up something like numpy, and here on numpy, so like we've got the documentation and so forth. Have a look at numerical computing tools. A powerful, oops, there we go, something's just jumped up. Okay, SQLite, and so forth. We don't need any of that. Try numpy. I think we're going to go for this, which is create a 2D array set every second. There's something like this. So I think it's just going to be an array. So documentation, getting started, to the guide, API reference, welcome to number, import numpy. So here we go, reading the code. What is the difference between a Python list and a numpy array? Enormous range of fast and efficient ways of creating arrays and manipulating numerical data, while a Python list can contain different data types within a single list. All the elements in a numpy array should be homogeneous. That means all of the same type. Mathematical operations meant to be performed to arrays will be extremely inefficient if the arrays weren't homogeneous. So that's kind of like the difference basically there. And here's the array, and we want a 2D array at least, or an ND array. So I think it is like this. What are the attributes of an array? So this is the numpy array here, and this looks like a one-dimensional array because it's just 1, 2, and 3. By the way, this looks like a list, so there's not that much difference structurally between arrays and lists, other than it's a contiguous block of memory, and it's a contiguous block of memory that's homogeneous in data type. That's basically what we're calling an array, as opposed to a list, which is just a set of items contained in a collection of some kind. So I'm just scrolling down, adding, removing, sorting elements. We're going to be doing some of this stuff. How do you know the shape and size of the array? And I think, well, it's a number of dimensions there. So I'm going to just attempt to create an array, basically. And let's just do it, really. So let's just make an array for a start. And we know that the length of it now is number of particles. That's the number of rows. So let's do create. But we can go into cheat mode as well, by the way. So I can go here. And what we're going to have, basically, we need something for, well, we can actually work out all of the components that we need because it's already been done. This is the nice thing about prototyping, really. Everything in our, where is it? Here, in our particle is what's going to go into the numpy array. So we need 3 things here for the x, y, and z component. Another one here, 3 more here, 3 more here, and 3 more here. So that's 3, 6, 9, 12, 14. So create a numpy array with 14 columns and n rows. Right. That's what we want. That's probably going to be relatively efficient. Comparatively speaking, it's going to be hugely efficient, actually. So let's have a look. Creates an array. Okay, so it is random integers. Okay, well, the reality is actually the random integer is going to suit us. So I should zoom in a bit. Control plus. There we go, just to see what it actually is, so that everyone can read this. But basically, it's this. It might be more or less. We might chop and change and add some columns. Where is it? Let's go there. Down, down, down. We might chop and change and add some columns, but the number of rows we do know because it's the number of particles, it's the number of stars in our galaxy. And even if one didn't exist, we would zero it out. So we wouldn't reduce the array size. It would just have 0 for the purpose of calculating. We'd give it 0 mass, for example. It wouldn't go into the mathematics. So, but this is quite useful because it's given us random integers. And the reason why it's useful is that in the original code, going over here, wherever we are in our simulation, one of the things that we do is we do get particles, and this returns a list of particles in the system. And if I go to the definition of get particles, oh, it's not the get particles one, it would be the one just before it, I think, possibly. Make particles, not get particles. But basically, one of the things that we do, and you can sort of like see it here, is random.randint, and we're kind of like assigning these values in some way, these random numbers, to create particles randomly distributed in space somehow with random velocities. But we've added a drift factor on there, but essentially it's random velocity, so they could be moving in any particular direction, although that's probably not like well, I think I should be giving them a general drift. I did actually put a drift component in afterwards just to try and see if I could make that simulation a bit better. So we'll muck away. Hopefully we'll get a better version of it. Random masses, random radiuses, and we spoke about the relationship between the mass and the radius. These two are in a way connected because they're connected by the density. Right. Although they'd be somewhat proportional to each other, and for the purpose of what we're doing, we might potentially drop it. I don't know. It's there anyway. It's going to be a column of data. That worst case scenario is we just don't use that column of data. So anyway, that's what that is. So, and those form the columns basically. And here, this like uglier looking structure, I was kind of like labeled the particles, but in our ND array, each row is going to represent one particle. So the first row will be row 0, whatever. It's going to be the first particle, and row 1, and row 2, row 3. So that's what we're going to have for our particles. So I think that should suffice. We're going to create a numpy array. I just put that down as a comment, but actually now we can go to Google Bard. I think this is correct, and it's going to create an array for us. So we'll give our name, the array, a better name. I wonder if we should call it particles. I can think about that. I'm going to call it the particle handler. There we go. Because I might call this the particle array or something. I'll call it particles for now. One of the things that we tend to do is we do things like for particle in particles. Right, it's a very common sort of like Pythonic pattern, and then we do something like, particles.append and particles.do this. But hopefully we're going to be able to avoid that, because we should be able to I'm not even going to say create an array, just create an array containing particle details. And what goes in here, instead of there being n, is, hold on, let's have a little look at that, rand int. Because in our little question, I just want to make sure that I get this right. In our little question to Bard, we said create an array with 14 columns and n rows. Okay, so it looks like what's going into here is a whole bunch of random variables, which is basically this stats k np.random.random, and then here we've got the size, and here we've got the type, all like so. Num particles, basically that should be the number of particles, and I think that might be good enough. And I just wonder actually if I can do like print what actually gets seen. And what I can do, because I'm doing this kind of like functionally here, well, I'm only calling the main module, right? And so let's just go to main, go to definition, and here we're doing the simulation, but I'm just going to bypass the simulation now and actually just go, because I just want to make sure visually that I get some sort of matrixy looking thing that looks correct. I'm going to call this particle handler, and we'll just say make a list of like 20 things wide. So this, and then the number of particles. I should actually set it to a default thing, because I have done in other places. I think I set it to a default of 100 in other places. So where was it? User position, connected particles. It was here. Number of particles. I integerized it to 100. We could just say we could default it to 100. If we didn't do anything, then you'll get an array of 100. So I need to put that down in here. Number of particles in. Okay, yeah, just you make it equal to 100. So it's got kind of like a default value, if it's there or not. So now we can call it, we'll get a list that's 100 long. And I believe that's everything, so that should just run. So if I hit F5, because what's going to happen is we run all the way down the code, everything gets read. So Python is aware of all of our functions that are available, but nothing actually happens until we hit line 156, and then it goes and runs main, and it runs the main function. The main function then calls at the moment, everything else is commented out, because it normally calls a simulation, it's just calling the particle handler. So in the particle handler, we should, when this print particles should return something. So I'll hit a 5 on that just to run it. And there we go. So I wonder if I can do Jupiter there. No, I can't because I haven't done it like that. So I might do it like that, do it that way. I could go to the debug console and have a better look at it, but actually particles, we could also print just to see what we get on here. Particles dot, and then I think it was endim, wasn't it? So endim. So I think that might work if I hit F5 again. Okay, that's the number of dimensions, which is just 2 dimensions, but that's just rows and columns basically, which is fine. I wonder how we get the number of rows. Particles, probably length of particles. There we go. F5. Yeah, so we get 100 of them. This bit here will be number of rows. So that's the actual particles, and also, well, the dimension bit is just 2, but that's because we've got a square matrix representing everything we need. We don't need anything more than a square matrix. So, because in this piece here, I've got some structured data, kind of like, I've created this particle object, and it's got things, and it actually got a little bit more complicated than needed for the sake of again, like, you can become clever, but then it costs you in terms of speed. So we're simplifying. We just got this array now. Now that's good. We got an array. We got 100 particles. But what we actually want to get is, I think we probably want to get not rand int, but maybe, well, we do want to get random integers, but I think we want to control them. And at the moment, everything's just between 0 and 100. So, which is a decent start, but actually we kind of like need to replicate this make particles bit here, where we want them between, in the space column. So we want to set certain columns to have certain random numbers and other ones to have other random numbers. So I'm probably going to look this up, but it will be, and instead of creating an array of random integers, create zeros. I think it's just np.zeros or something like that. I wonder if it's understood what I've said. I've become so lazy with these helpers. Yeah, it's just np.zeros. Right. So it's a little bit easier. We will use this random thing, but we need to control it a bit better. So here it'll just be, I can delete all of that. Well, in fact, what I'll do is I think I'll take all of this and paste that all here, and this n will be number of particles, and this one here will be our columns. We'll say there's 14 columns, but we need to specify that. Right. And I'm just going to read this. Sure, here's how you can create an array of zeros. Just want to make sure that that is correct. The code will first import the numpy module, then it will define an array of zeros. Here we go. It takes two integers n and m as inputs and returns a numpy array with n rows. So that's what we want, number of rows, and then m columns. So the first argument is the number of rows, and the second argument is the number of columns. And it will just be a bunch of zeros that are created at this point, and then it's for us to fill out. So we've got number of particles, and then column 14 there. I wonder, because I think that maybe a pandas data frame might be even more suitable because we can label our column headers. Pandas just builds on numpy, but what I'm just thinking, because how do we reference? I'm just wondering the fastest way of reference, how to reference. Because numpy arrays don't have column headers, and we are going to need column headers, or it's going to be helpful to have column headers, that's for sure. I don't think they do numpy arrays have column. The numpy arrays have column headers. There we go. I think this is where pandas is going to come in. No, numpy arrays do not have column headers. Numpy arrays are a simple collection of numbers, and they do not have. So this is just for pure number crunching. However, you can add column headers to a number array by using a Python dictionary. For example, the following code will create a number array with 10 rows and 5 columns. I think that's, which is okay, but basically pandas is going to do that. So what we're going to do is, I'll probably end up back at the trio. Over here, we might do import pandas as PT. Right. These two nearly always go side by side, actually, but we're not going to import, or we're not going to, the pandas data frame contains, or it lives on top of numpy basically, so it uses numpy functionality. So we're going to go that way now. So in our, because I had a to-do list or whatever, create numpy, and it's not a pygame array anymore anyway, because I was looking through the documentation for pygame, which was here, and I thought, because I saw SND array, and I thought that's like an ND array or something like that. That's what I thought. And then I went to have a look, and SND stands for sound samples to an array. So it is an array of some kind, but sound array. I don't think it's not the arrays that I thought that they were going to be talking about, at least. So we're back onto, I think a lot of Pythonic type of stuff ends up going back to pandas and numpy and pandas. So that's where we're going to be. If we, a lot of the operations on pandas, I actually found pandas much easier to work with. A lot of the operations on pandas are very similar to numpy, but you get the column headers, which is quite useful. And we're going to sort of like need that in a way, because otherwise we're going to have to remember the linkage between them. Now, it did suggest here in Google Bard that you could cross-reference them effectively, but if we're going to do the cross-referencing, then we might as well just use pandas. And so where would we use a numpy array compared to where we would use pandas is somewhere where, I guess, where you're just purely doing the number crunching, and you want to transform an array or something like that, where the column headers aren't of any importance. But here the column headers are telling us something quite useful, which is it's giving us our positions, our velocities, our masses. So we're going to have a column header called mass, and we're going to have one called radius, and we're going to have one called positions, position X, position Y, position Z. We're going to have that. And the same thing for velocities, and then also somewhere else, wherever we make our other components, which is, so actually everything in our particles array, we're going to have 3 positions, because we've got X, Y, and Z components there. Although we're only using X and Y's, we've got 1 radius, 1 mass, 3 velocities, 3 forces, and 3 accelerations. These are linked to each other. Well, the force and acceleration linked to each other, and that's used to compute the velocity. But anyway, that's what it is. So I'll go from there, basically. So let's just do that. So I turn it into a pandas now, because that's what we're going to do to create a numpy pandas array. And we've actually turned around and said we're going to create a numpy pandas array. So let's just do that. So again, this is all live, so I'm kind of like deciding this like live as we go along. So it's no longer MP zeros. It's going to be this is much more common, right? You just say data frame, because it's a pandas data frame, equals pd dot data frame. Okay, something like this. Now, how do we populate a data frame? This bit we can do a little bit slower, because the initial setup of the data frame for the first run when we construct it, so I might have a constructor for a data frame, so long as you don't operate on it, it's going to be, I think it's a dictionary of lists, basically, is the most convenient way of doing it. Now, it'll be slow initially to construct it, because we're going to pass a list in, but once it's in there, the data frame is going to be quite efficient. So it'll be something like data, or we could say stars or particles. So instead of having this particles now, comment all of that out, we'll have particles, and we still construct the same data. So it's going to be a dictionary, right? It's going to look like this, right? The keys of the dictionary, and I possibly should have done this anyway, but the keys of the dictionary now are going to be all of these parameters here. So they will be pos, right? That's the first. So I've got to do keys, right? And it'll be a list, right? But it's actually going to be the pos x. It's going to be the first one, right? So our dictionary is going to be relatively lengthy, because it's going to be like 14 columns long. It's going to be everything that we want. So actually this is going to form itself quite nicely. This is live thinking. Pos y. I could be doing this wrong. I might invite some people in here. I could be doing this wrong, but I'm hoping. But I think that it will be better. And pos z. So that's the first thing that we want. Right. The next thing that we want is the radius, and mass. I could put the positions, the velocities, the forces, and the accelerations all together because they're all the three types of, they're all the things that need 3D stuff. So I might put maybe a radius, mass, and velocity first. Not that it makes a huge difference because we're now looking at homogeneous or heterogeneous, I think it will. The pandas data frame is heterogeneous, which means it's got the columns have homogeneous data in it, but each of the data things could be different between themselves, although in our case I don't think they will. So be fully homogeneous in a way. Let's just do this pause. So let's just we'll take radius and mass first. So we'll have radius, and we're going to have over here mass. I wonder if even, well, in theory we could have an index, but the reality is we don't need an index because the pandas data frame has its own index. So again, it's kind of like something that I created that was overkill. So we've got radius and a mass. Then we got our position, and now we can start doing, well, I can copy a lot of this down, I guess, because we've got positions, and the next thing, copy these. I'm just going to turn them into velocities, basically. So velocity, velocity, and velocity, right. Go back here, and then we've got force and acceleration. So same thing again, copy this, paste it, force, 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 and then finally paste the last one, acceleration, acceleration. And I guess in having constructed this, now you can sort of like see what, what's the difference between this dictionary and this particle here, this class, because a class actually creates a dictionary. It's a bit more structured, and you get to see all of these things basically, and sort of like how you're constructing it, and a little bit of help. But again, it's kind of like this nicety is costing us computational complexity. Now we could take the whole particle class, we could do that and actually pass it straight into this dictionary, so you could like do the construction of it. I'm wondering if I should do that and then pass everything straight into the dictionary. Because the reason why, there's no harm in actually having it. I wonder if it's easy to do that, because then I could do something like, well, have you got the representation of it? I could steal this piece of code, this class, and then here where we've got this make particles, I could do all of the making of the particles and then pass, because what's going to happen is that once they're made, they're going to exist in the dictionary, and then pass this entire pass this in, like each one of these, into their respective pandas data frame columns. So I could do that. And that would have the advantage of being relatively, I guess, kind of like nice. I might make that anyway. I'll just take, given that it's written already, what I will do is I will still take this particle class because it's been coded for already. And I'll take this representation of it as well. Copy that. There we go. Because it's quite nice. So we've got our particle class, and I will just stick it here. There we go. we've got a particle class. Now, okay, space 3D. Okay, if I've got a particles class, then I need this bit here, which is space 3D, which describes our space in 3 dimensions, which is very similar to what pygame offered, because it had a vector 2D somewhere above wherever we were doing it. So we did have a vector 2D somewhere. I think it's here. Yeah, vector 2. And vector 2 is a class which just contains the x component and the y component, and they're both floats. So it's ironically, it's very similar looking to the space 3D class that I made, that although maybe it's got other features in the pygame version, it might have other features that I'm unaware of at this point in time, which might be more beneficial. But anyway, we've now got a 3D class. So we've got a way of just talking about 3 dimensions. And also in doing this, I will take these bits here and move them up, or I'll move this position down. Position's really the most important thing, to be fair, right? But I just put these here because these are single values, and these are all 3D values afterwards. So it's just kind of like ordering them relatively nicely. And if I ordered them there, then I guess I should just move it down the list here. So position comes before velocity. So I think that will do. I don't know if we'll do, like, because we're basically in the process of constructing, because we've got to construct these now. Now, I can just do something like x for x in range and then our range is going to be what a number of particles. But here we're not just going to do x, we're going to do well, I guess rand int. Well, yeah, in fact, that's what we will do. Well, for now, we could actually make these all the same. So, which bit was I talking about there? Okay, for the radius, our radiuses here are just between 1 and 10. It's just a random dot rand int. And you know, the convention is to use underscore in range number. I'm just wondering if there's a better way of constructing that. This is just a list comprehension, it's fine. We're only going to run it once, so we're only going to have one setup cost for that. It won't affect the simulation afterwards, because the simulation afterwards will just be simulating on the existing particles data frame. So we're going to pass all of this dictionary into a data frame, and that will be vectorized. I just want to do this, which is basically create a list of integers between 1 and 10 of 100 random integers between 1 and 10 in Python. I just wonder what it spits out. It might just be that this is kind of like relatively the fastest sort of way of doing it. Well, it's actually made a function there. Don't want to do that. I was hoping to do using because it's one-liner if you use list comprehension, and it's actually faster. I'm not sure why. Why did it do that? Import random, create list of random numbers. Okay. list of random numbers equals, okay. Oh, it has, was that the new bit? Okay. That's kind of like what I was expecting, which is random.rand in min val max val for underscore in range n. If double, okay, fine, that's just the other bit of it. So what was this doing? Oh, okay, fine. It wasn't doing a list comprehension, it was doing the classic for loop, which is actually slower and longer. So this is a classic case of where you use list comprehension. So this is pretty much the kind of fastest way of doing it. So fine, we'll just do that. And we need to populate each of these. So we're going to have to do a similar thing here. And all of the rules, again, the rules that we're making are just like things that I made up. So really, like, you'd want to collect your data and kind of like pass it in some way. But in order to populate, we have to have something. So something that has some relative common sense. So we've done the radiuses, and then we had the masses. And I just said that they're random integers between 1 and 100. I think I was mucking around with it, but like wanted a bit more diversity. The reality is if you're going between stars, it might be something like between 1 and 1,000. But then we'd only do that when a number of particles got bigger. So for the most part, because you can imagine, like, if we had 100 particles and one particle was size 100, it'd be, and all the other ones just randomly, coincidentally, were really, really low numbers. It'd be like roughly 50% of the weighting, and so everything would be rotating around that one big particle. So we don't want to distribute, at least to start with, we don't want the distribution to be too wide, but that'll be between 1 and 100. And also, like, in terms of selection, I didn't want a zero mass. I went through that in another reason why, but basically force equals mass times acceleration. So force divided by mass is acceleration. If you've got zero mass particle, you've got an infinite acceleration. It'll break our code. So we can't. So I kind of like to let's just start with this, like some useful numbers. And the same thing here. We don't even use radius, but if we were to, and you were to anywhere divide by a radius, then you would end up getting an infinity. And so let's not have zero radius planets or stars. If the planet is of zero radius, we'll say it's not a planet or a star. There you go. So we go back here, and this was between 1 and 100. You can see why this is relatively convenient, although I'm going to have to go through each one of these. For the positions, they were all between minus 100 and plus 100, and that's to start them kind of like, I guess, symmetrically around the 0 point. But actually I shift, our 0 point is the middle of the screen. So we shift everything across, so because our 0 point is really, that's our screen width and height, and our 0 point is half of this. So 1 to 80 was at 640, I guess, and that's 360. That's what our halfway point is, which is what this thing should give us, the width divided by 2 and the height divided by 2. So really I could stick that in there, but we do a shift of everything. Now I've added computations to it, so I'm hoping that the efficiencies that we get mean I don't have to like be even more efficient. I would like to not have to think about it too much. I hope some of it falls in place. But anyway, so that is basically that. And it goes between minus 100 and 100. And I wonder if we could just say that pos y is equal to pos x. I don't know. I could set this out at the top just above it and then have like 3 random integers, but then I'd need to have them for everything. So it doesn't matter, let's just do the construction. I'll keep doing it. So that one's the same and that one's the same, and then for the velocities, do we in our construction mat make particles? We've got the velocities, and I've actually added a drift component on there. So I'm going to do a random integer of minus 10 to plus 10, but then I would add something on, which we can do quite simply. So again, we can take all of this, actually, we can use it, which is this, but instead of being that. So our particles, our planets or our stars, can go in any direction in the X, Y, and Z component. So that, but we're going to add on a drift. So I have to create a drift. Right. So it's going to look like that now, which is fine. That's good. The list comprehension is quite condensed, so it's sort of like relatively nice. And then this one. So we've got these particles, but on average, they're moving in that way. Now I could have just gone, well, you could ask, why don't you just go 0, 20, 0, 20, 0, 20 instead of doing minus 10, 10, and then do it, and then imposing a drift. I don't know. It's kind of like either or works. Now for the forces, it's just 0. I think we set no forces to start with initially, and then the forces are going to get computed afterwards. So for the forces, it'll just be 0 for underscore in range. I'm going to be careful about all of this because I don't want any of the pop-ups to come. Number. Right. And also the same for the accelerations. We've got no acceleration to start with. Now we could say that's wrong. You should have some accelerations, but for the purpose that they will get computed on the first iteration when we have our forces, we can, and we've given that we've got our masses, we can then calculate our accelerations. And where do we get our forces from? They will get computed in the first iteration too, because we know that force equals, or sorry, we know that force equals minus GNM over R squared, which is from the classical. We're using classical Newtonian mechanics for this bit, so every part of this we'll be able to compute in our next step. So this is kind of like our first iteration. It's sort of like our constructor. We've constructed a galaxy that looks very similar to, well, nearly, well, in fact, identical to this galaxy that's been constructed, but we're not using a class to define it anymore of type part. We're not using a class of type particle to define it. We're just passing everything straight into the pandas data frame, so keeping it all quite simple, simplistic. Now, what do we do here? All we have to do is particles. There we go. And that should be everything. That'll pass it all into data frame, and we can print the data frame. In fact, not only can we print data frame, I think we can do data frame dots, what's the things on its data frame, like an example of, we could do data frame df.head, df.tail. There are two things that we can do, but we can also do like a summary. And again, summary of a pandas data frame. I can't remember what the thing is. I stopped remembering nearly everything because all of the help tools and everything are better. Basically what you need to know is how to ask for things. Oh yeah, df.info, that's the one I want. So we'll just do that .info. This is a masterclass in things that we can't like remember, that I can't like remember, that we want to pull out. But that should print us, get something. So let's just run this, F5, running it. And I might need to expand it. We'll see what comes out. Ooh, memory usage. That's quite interesting. We use 11 kilobytes data. And what it tells us all of our columns. We've got columns here. Column, not null, counts. So it's looking like, you can consider this like the pandas data frame to be a bit like a database, effectively. But we can't see the data per se in any one thing, but we can see the type. These are all in 64s. So it's now, and we could change the D type, I think, to like something a bit more efficient, like a smaller number. I wonder if this one here, because could we go down to D type in 32? It's like saving ourselves some time. In Python here, it represents a signed integer with 64 bits. And this is the thing about speed, right? We just need numbers, I think. This data just needs numbers that are like 32 bits or 8 bits, because all we're talking about is distances. Can they go to these extravagantly big numbers? Because we've just got our screen at like 1250. Can it be bigger? You know, do we need to have this big number? So is there is a D type 32 question mark, right? We want a bit more efficiency. So here's a good place to increase efficiency. A nice big gain. Yes, there is a D type 32. This means that the D type data, okay. And nothing that we have, like everything that we have here is literally like, so we can halve our memory usage and probably increasing the speed as well, I imagine. So from to, oh, sorry, from int 64 to from let's just see, I'm hoping that it will just be something like .2 in 32 or something like that. Yeah, I wonder if I can do that on the whole data frame rather than just on a column. So I don't know if this will crash or not. No, it works, perfect, fantastic. Memory usage 5.6. We've just halved everything in size. And again, if I go there, I just wondering how big the number is, but I think it should be more than big enough for our representations. We could always switch back. It's just like an optional extra that I just thought to add on. So Python 32 is a signed integer with 32 bits, and this is like it goes up to 2 billion. 1, 2, 3. Oops. Double click it. There's 3 there, 3 there, 3 there. So it's 2 billion basically. So from minus 2 billion to plus 2 billion. Whereas this one went from, oh, that's also 32. Okay, the 64-bit one that's a billion. So it's like a billion billions. Just a lot bigger. We don't need that to start with. Let's just see what we can get out of this. So that's kind of like a very, very quick free gain. So that's basically it. We've now gone from something quite more complicated to something relatively simplistic. And we can do print df.head. It defaults to the top 5 rows. I believe, and the f.tail as well. And somewhere in between is print. Right, something like that. Right, so F5 to run it all. And we'll get the header and the tail as well. So this is kind of like what it looks like, which is quite nice because we can see a lot of our data. That's the memory usage. Why we only see like little bits of it? I was hoping to see more of the header. Why does the tail come out first or something? No, I wonder. Print df.head. And then the triple dot df.tail. I'm just going to move this print because I just want to see everything basically. Tag that and paste that there. Run it again. Okay, now it's clear. Maybe, I don't know, maybe it got overwritten or something on the last one. Possibly, I don't know. But there we go. So we can sort of like see we've got a whole bunch of radiuses. Our radiuses are between 1 and 10. So this all looks really, really good. Our masses, they're all between 1 and 100. So it looks good. Our x positions, our positions in space. So these are our three coordinates, the x coordinate, the y coordinate, the z coordinate, and then likewise velocity, and then there's these triple dots. It doesn't come out on a Jupyter, it won't come out in Jupyter variables because I haven't run it that way, but there'll be all of the other components of it. So, and then we can see the acceleration in x, y, and z, they're all zeros, the forces in x, y, and z, they're all zeros. So exactly as we wanted. So that's looking good now. So that's our particle handler. Now I'll need to feed that into our list, into the main function. So I'm kind of like comment this out. Don't need that. Don't need that anymore. This stuff here we can actually remove. So I'm going to keep these commented bits because they are descriptive. Basically, if show description equals true, right? I'll just do show description equals false, basically. I don't even need to put the equals true. We'll create this boolean, and we don't even need to do the equals. If show description, then kind of like show description, but we're not going to show the description, at least for now. But if we wanted to, it's there. So we can just set this one to false. There we go. So that's a complete function. It's isolated. It's on its own. Number of particles. Is there anything else that we wanted to put in? Not really. But this is now make an array for them. Make an array. Make a pandas data frame. So there we go, make a pandas data frame containing all the particles. So that's everything. Now what are we going to do with that? Okay, well the first thing we're going to do is return the data frame. There we go, and life is much easier because now this thing here is just going to return a, in fact the type hinting of it will already come up because it should know it, but it says data frame. But a pandas data frame. Okay, we've said what it's going to be, but anyway, it's going to be that because Python recognised it because it knows the return variable here is of type data frame because df is a data frame here. We've kind of constructed it and made it. But this is now a well-formed function. This is actually a really well-formed function. I should have done this maybe in the beginning, who knows. So I'll hit save. Nothing's going to happen yet. We need to now put our particles there. Now, one thing I might do, I want to keep creating the list, so I've got to be careful about this, is basically, so here we're going to run our simulation again, and here we can comment this out because it's a particle handler. We're going to call this particle handler now somewhere potentially in our simulation, which is just here. Create a numpy or pandas array, and we are now going to call what we call particle handler. There we go, and it automatically takes 100 data points in there. And this is before the while loop starts running. So, but what it's going to give us back a data frame of all of our particles. And I'm just wondering, but actually it doesn't really, because we've got the number of these connected particles. This was our other function where we sort of like tested connected particles. I'm just going to go, I guess here, number of particles. You know, it was going to default to 100. We could still stick it at 100. There's nothing wrong with that. But what actually I want to do is to get this into our... The question is how do I get this onto the screen? So that's our data frame, and it's been constructed. It's returned that. So now we've got data. In our connected particles thing, what will we do there? I could hover over it because I've documented it. It returns us nothing. This one returns us nothing back. So, but okay, it does draw to the screen. So here now, we're going to need a method to draw to the screen. So we need in our to-do list, what we need to do is draw a pandas data frame to the pygame screen. That's what we're going to do, at least to start with. Now our dots or our particles won't be moving, they're going to be static because we will create one random version of it. But what we want to do is get this onto the screen. So we're going to have like a draw to screen function, is I reckon is what we're going to have. And the draw to screen function is going to take in a screen. So we're going to need a draw to screen function. And down below, def function draw to screen without a space there. Right, it's going to take in a screen, and it's going to take in a pandas data frame. Right, so we know that one. It's going to take in a screen as well. We know what the screen thing is because I'm just going to copy it from somewhere else. We've got a write to screen as well, by the way, but that one takes in. Yeah, I think it's still the same thing. It's a screen. It's the pygame.surface.surface thing, which is this bit here is what we want. So that was our right to screen, but I wonder if do we have the user positions at that one also did I took that one in. The position of the users on screen. That was for controlling the big white blob that was in the middle of everything. And we are going to go here and stick this in. This is our type hint basically. It's quite a large chunky type. These are big fat type hints, right? Look at that. That's what you call a type, a data type. Python lets you focus on data types. That's one advantage, right? So what we're going to draw is given a pygame screen and given a pygame surface, I just call it surface, and pandas data frame, draw particles. There we go. Right. And basically, well, args, we kind of like know what these are because we've type hinted to them anyway. This df here is a right, it's a pandas data frame containing all the data on the particles, and the other one is the screen. It's just our pygame screen surface, which I do like to copy this because I have to remind myself 1,000 times. But basically, we need this. Right, that's necessary. So the args. Are we going to return anything back? Possibly not. I think we're just going to write to it. So now, how do we draw to the screen? Let's just go and get a reminder for drawing to the screen. There we go. I believe that will be something like this. But our X and Y components will not be X, that they will be from the pandas data frame. So now I want to draw these quickly to the screen, so I'm going to have to do some testing. This is a thing. This is all live now. Right. Draw circle. So the first thing is the surface. Well, that's a screen. Then a color. Then the coordinate. And then the radius. But the radius here is going to be the data frame and the radius column of the data frame. So here will be df. Now, can I pass in an entire data frame into a pygame draw and have it draw like all the circles all in one go? Super quick. So I don't know. Like, I've not done that before and I've not heard of it before, but it must be doable because that would make things very fast. How to put a column into a pygame circle. I don't know if this question is going to be good enough. I wonder. Because what I'm thinking is I should just, basically what's going to come into here is I should be able to just call this, which is particles.radius basically. Well, not particles.radius, but data frame, df radius. So that should be what I should be able to do. And likewise, this will be df quotations, and it's going to be the pos x. I like to copy and paste because then it saves typos, and this bit here would be pos y. Now, that would be ideal if you could just pass that entire thing in and have a 100 drawn, because that's what it is, and that's vectorizing. I don't know if it allows. Let's just have a look and see what comes back from here. Sure, here is how you can put a pandas column containing all of this into a thing. Okay, but then it goes and does a for loop. So create a list of Python circle objects, because I don't want to do it by list. I want to do it vectorized. I don't know if it will or won't. There's one alternative to doing this, to getting it vectorized, which is something like a df.apply on the column, and then apply the and then apply all of this to that column, to the columns. I don't know if that will work. Have a look here. Create object. I mean, this is ugly. This is like third best choice. Doing that, definitely want to avoid it. That was a whole point in the beginning. Because we'd lose. I just think there'd be a huge gain in speed if we could pass all of these objects in one go. But I don't know if they can, if it can be done like that or not. I could write a Stack Overflow question. I wonder if that's been done. Google it. Let's have a look. How to put a pandas column. No, so none of these questions are going to be relevant. How do you draw a circle in pygame? No. Okay, how do you put a pandas column? I'll do that one again, basically, which is into in a vectorized way. I've just asked the question. I don't know if it's doable, but I'd hope it is, but I don't know. I spelled vectorized with the English version using an S. Should be Z for the US American version. Corrected it there anyway, so it's recognised it. Okay, but it's, I still see. I do see for circling circles, so that's possibly not good. Let's have a look. DF create. Okay. That one's interesting. Create circle object vectorized. XY is the DF location of the X posits and DF location of the Y posits, which is fine. Circle object. Right. I mean, possibly here. Circle objects and then return circle objects. Well, certainly one thing's for sure actually is I could do a list comprehension instead of a for loop. So I wonder if that's the case. I might leave it at this point, but I definitely something to think about, which is basically going over here on this bit and draw to screen where I might try and do the slow method first in a for loop and then modify it, iterate towards modifying it to a fast version. But I really need this to be fast because if I'm going to do it, I need to do it properly. So I need to get a fast version. Because the slower version will be something like for I in range. Oops, all of that. And then this will be the length of the data frame. Len of data frame, and then that would be something like this, where now would be df, and I think I wonder if I have to use a location or if I could just do df posx and then sort of like I, and then this one here would be I, and then this one here would be I. And then this is the slow method. This is not what I want to do. I want to do a vectorized version of it. But I just wonder anyway if this will actually work. Because we've got a surface. So that's going in. Then we've got our colours. And then we've got our X positions and our Y positions and our radiuses over there. And that should be sufficient for the draw. So we could do it. I'm just going to attempt to do the draw to screen, I guess. So it'll be over here. Right, not this right to screen, but over here, connected particles, draw that. So this, draw to screen, and then screen. So that one's easy. And then, well, actually, this one's easy as well. Well, it will be easy if we created the data frame. But we have created a data frame because it's over there, so that's fine. Right. Now, it's going to keep drawing it. I had to put it inside the loop because otherwise, you did, even if it did work, I don't know if it's going to work, but even if it did work, you get one draw and then the next loop over would go and fill it back with black. And that's why you have to keep drawing it because the black would just go over the top of it. So let's just attempt to run this anyway and see what happens. F5. I've got no idea. This is live. Okay, so something's happening. That's good. I know it's good and it's not good because I don't know what all of this is here. This white blodgy stuff, and this is the random dots. And I don't think we're expecting random dots, but is that because we've got this connected particles bit here? So that was the random dot. So if I get this one out and then run it, we're probably just going to have the horizontal lines. Now that's a bit ugly. Anyway, that part works. But yeah, we've got these ugly look. Oh, I can see some dots there, funnily enough. So something's happening. Just in that strip. It's going to close in a second. I wonder if I do it a second time and see what happens. F5. Maybe I'll make fewer dots. There'll be fewer lines. Okay, I see another dot just protruding its head out there. So there's some hope for this. So, number of particles, we'll just make it 10. Just see what happens now. Right, so something's happening there. Again, we're getting these lines across the screen. So, and what's interesting, okay, I haven't done any of this shifting or anything like that. That's why they're all clustered over there. Because one of the things that happens is that we need to adjust, and that's what does happen in this bit here where we've got the connected particles, is I believe that we make an adjustment for the position. So if I go to the connected particles piece here, we draw that and that, but it's okay, we got the screen width there. And this is because we're allocating for the screen width, whereas what we're doing on our pandas data frame connecting thing here is we've just done this number of this thing here. So actually what we're going to need to have to do is adjust for the positions not to be minus, or if we do this, that we need to adjust for the screen width part of it. So I would need to pass in the screen details in that respect, at least to get them on the screen. So that's something to think about there, because these are just going to be, maybe these lines is the X pos and the Y pos is where I got, maybe where, if I just comment these out, right, because our screen size basically, we know our X position is basically 0 to, or our X coordinates, at least visually to see, is between 0 and whatever that we said it was here. So I could really pass this in width and height there. So 1280 and then 720. So that's what the limits are for those. So that could have been potentially the error. 1280, and this one here is going to be 720. Right. Now, these ones here, the Z positions don't really matter in that sense, because it doesn't matter what they are, because they're not getting drawn to the screen. But these two definitely matter for the purpose of visualizations, and if I just do that, I wonder if that works a little bit better. Yes, it does. Okay, and we don't get those lines as well. So that's potentially the answer to why the lines have come about. Somehow, it's really weird, because it's almost like as a dot's like being completed all the way across something, I don't know. But anyway, this is kind of like working, but in order for this to work, we have needed to know the height and the width, and so I have to think about that, because we don't want any hard-coded numbers in here. Or at least we can still have 100 and 100, but we need to do calibrations. Now, we basically need to add on in our drawing of the objects half the height and half the width. So in our, wherever it was, back up here, in our draw to screen, we've got our data frame, but actually we need to know the, in fact, in our screen thing, I think we get these calculations will be because it's part of the screen thing, so we don't need to pass a height and a width in, because they're already passed in. So if I go to this draw to screen function, go to definition, we can actually pre-compute those because we've got those here. right? And then we could add them on here, plus W underscore center. So the center width, and what I'm going to do here is just move this all because it's getting a bit big. And here for this tuple, plus H center. Right. So it's a little bit clearer, hopefully now. We get our screen, we've got the yellow dots, we could have random coloured dots, whatever, the yellow for now, and we're adding on the center point. Let's put spaces so it's nice and clear, and our width center, we're adjusting all of our X positions by this width center, because if we had something at minus 100, and that's probably why we get the line across, because negative 100 has no meaning for an X, nor does it have a meaning, by the way, for a Y. And that might have been the case of where the lines were being drawn across the screen. I wonder if that's the case, because it worked on a laptop, funnily enough. But if I do F5 now to run it all, I'm hoping that that should be sufficient to fix. And it is. There we go. Everything's all like clustered. They're all clustered relatively in the middle. The dispersion isn't wide enough. And because all I've done is add on a sentence, everything's between plus or minus 100. But we know that our screen width is much wider. So I'll just F5 again, run it again, because it wasn't in the middle of the screen. Everything's kind of like here, and if I'm quick enough to draw, everything's sort of like clustered in this little center part. And that's because it's between like 100 and like, that's 100. And that's minus 100 over here. It's going to disappear in a few seconds. Loop, whatever. I wonder if I can loop. But that was basically it. So we could actually, I need to think about how to scale that. But then things are going to drift away, they're going to move. So maybe I won't, because they'll go off the screen anyway. So we want our things to be there. But now I can actually go back to where we called it, and instead of having just 10 dots, we can go back to having 100 dots. That will be fine. So in our data frame that we create, let's create 100 particles, F5, and run it. And there we go. Notice the box that it starts in. It's kind of like really, really, really bounded. And yeah, I can move this around, funnily enough. But the box is really, really bounded at this point in time. That's sort of like where it starts. So it's all clustered, and it's clustered in a square, which isn't like, you know, the greatest clustering. Maybe I should do like a normal distribution, like a log normal distribution. So the clustering is sort of like more distributed, like what galaxy is. So I've got like I've got a square. I've created a square galaxy. Like we want like a spiral galaxy or something like that, or something where there's high density in the middle and so like lower densities outside. But anyway, we've got this working. That's quite nice. A lot of ground is made because we've done that. And now the great bit about this, so is this is kind of like created because it's here, is we can now move on to manipulating here. Draw to screen. We've got our draw to screen function. Given any data frame, we can draw to screen. And what we need to do is just go and modify the data frame. So this function here is just like a constructor, basically, particle, maybe I should call it constructor. It makes the original data frame. We need some sort of feed to have just the framework that contains enough information for us to do our computations on. And then once we've had that, once we've got that, we can then do an operation on it. So now we need to be able to operate on a data frame. So the function, I'm going to call this evolve. Particles. Particles. Right, and it's going to take in a pandas data frame just like that. I think that's all it probably needs to do. It doesn't even need number of particles now, because it's going to be fed effectively with a data frame, so which is a of type pd dot data frame. Right, so we need to fill out this function, so do the physics to So we need to do the physics to evolve the universe of the particles. That's what needs to be done in here, and we are going to return df, right? So it's going to take in a data frame, and it's going to effectively take in the data frame, modifies the data frame. So args, it's going to take in a df, which is just a, and then it's going to return the now this should work. This should work really good. This piece will be quite fast. We should be able to do all the vectorizations in this relatively quickly. But the one bit that needs to be investigated is this draw to screen function, because at the moment, and we needed to do, this works, it's okay, but we want to, so to do, right, we want to vectorize, we want to vectorize the above for loop. If we can, that's what we want to do. So we don't want to iterate through each item of a list passing in data. We kind of want to push our contiguous block of data straight into the pygame, and I don't know if that can or can't be done. I need to do some research on it. I could do some live research. I think the live research will be a time killer, so I need to just have a little think about that really. If we can do that, this would be super fast, right? I don't think I've created the new concept of like gaming, but basically if I had a gamer's mindset on for like a game builder, game creator's mindset on for constructing the data, if I did have that mindset on, I would certainly want to be able to pass my simulation parameters into the system much faster. Maybe it's a case of not drawing circles, maybe it's a case of something else, I don't know, but I have to have a good think about that. So that's definitely on the to-do list there, and our other thing is not really actually on the to-do list per se, but it needs to be completed because this is our physics, basically evolve the particles. Do the physics to evolve the universe of particles. Return, well, okay, and return the evolved. What we do know is that we're working in a data frame, and it's natural to do everything in a vectorized way. So these calculations will be super fast. So that's good. And I think I might leave everything there because this has been going on for a relatively longish time. I wonder how long it has been going on for. God knows. Let's have a look down there. How long have we been going on for? Oh, nearly 2 hours. So I'm going to stop the stream. If you can like it, thumbs up. If you've got any comments, I don't think I looked at any comments, or possibly I did. Ah, Zio. Hey, welcome on board. My only views for my nephew. Shout out to Zio, the Kingfisher. That's basically it. I think I'm going to leave it there and sign off. I can see that you're not currently viewing, but you're welcome to come back. But yeah, if you do, like, you could like this, thumbs up, comments, whatever you want, and yeah, we'll see what happens from there. So that's it. I'm going to end the stream.